All right, for extra problems on Newton's laws, just in case you bump into one of these, you should be able to tackle them. So take this problem. Here is a box of 10 kilograms, and it is sitting on a rough surface. The coefficient of kinetic friction is, let's say, 0.3. The coefficient of kinetic friction is 0.3. And this box is being dragged by someone by a cable attached here. So somebody is applying a force in that direction at an angle of, let's say, 40 degrees. So do you understand the scenario clearly? So it is an object sitting on a surface, and you're pulling it using a cable or something like that. You're pulling it at that special angle, at 40 degrees. So when you're pulling it at that angle, let's say it is moving and it is accelerating. What is its acceleration? So that's basically the question. What is the acceleration of the object in this particular situation? Okay. So as usual, what you need to do is first draw the diagram, and the diagram is already there. And then we have to discuss about what forces are actually going to be acting on this object. So start naming the forces. Gravitational force. As I said earlier, gravity is an entity. It is not a force. Okay? So don't call out gravity as a force. It is a gravitational force, or simply say weight or something like that. If you say gravity, mechanics is a topic. Gravity is a topic. Light is a topic. Speed of light, intensity of light, those are distinct quantities. You understand? So yeah, stating gravity as an answer, although it's understandable, it is not the right term. Okay, so the gravitational force. We're talking about forces. So what is the gravitational force here? 98 newtons. You already know this, that gravitational force is weight, which is m times mass times gravity. And then, what else is acting on it? The normal force. The normal force, is it equal to 98?
Yes.
You always think like that, but I'm not calling it 98 so far. I'm not taking it as 98. And you'll see the reasons why. What else is acting on it? Yeah, there's 100 newtons acting on it here. Yeah, there's 100 newton. Well, that's given in the problem, okay? That's part of the problem. 100 newton is the applied force. What else is acting on it? There is friction, yeah, there's a kinetic friction that's coming in, which is Fk, which is mu k times normal force, normal reaction. Any other forces? Yeah. Now, all the forces are done. But before we go to the next step, we have to resolve this force. Because that's a force that is at an angle, and we don't want to kind of mess with that. So we want to split it into how much of this force is dragging it horizontally, and how much of that force is dragging it vertically, right? Or pulling it vertically. So we need the components. What is the component of 100 in that direction? 100 what? Cosine 40, tell me. 100 cosine 40, how much is that? How much? 76.6 newtons. And what is this component? 100 sine 40, which is 64.3. Write your newtons, units everywhere. So now we have split that force and there's nothing else that we have to do. Then we start thinking of application of Newton's laws. Now we're going to apply Newton's laws. Now, this object, is it kind of moving upward or downward? Generally, you don't expect it to happen, right? So when you're trying to pull a box or something like that with a cable, unless the pulling force is so strong that this force is bigger than 98, then it'll just come off from the floor, right? If you're applying too much of a force. But this force is not strong enough, you can see this. What is the component acting on the box from your pull? Only that much. So it is definitely not going to raise the box. The box is still going to be there. So when you apply Newton's laws to this box in the vertical direction, which law are you going to apply? First or second? The first law. Why? Because this block is neither going vertically up or down. It's on the table, right? It's on the floor. And so this box, you can apply Newton's first law in the direction. So net force in the y direction is equal to 0 because you know it is not moving vertically. Net force in the y direction is 0. So how do you take all the net force in the y direction? How many forces are acting on it? So there is NR acting upward. Positive, negative? Positive. So NR, positive. What about this? Negative 98. Any other vertical force acting on the box? Third one. A part of your pull is acting upward. It's plus 64.3 is equal to 0. So what does that tell you? NR is equal to how much? What is NR equal to?
$33.
98 minus how much?
33.7.
33.7 newtons. That's what you'll get NR as. So unlike earlier problems where you just blindly took NR as the weight, you can't jump to the conclusion here. You understand? Because this thing can contribute a little bit upward. So when you're trying to pull from this angle, you are trying to lift it off the floor a little. You're trying to lift it off the floor. That means you're trying to relieve this book from making a full impact on the table. So instead of pushing the table with 98 newtons, it's only pushing with 33.7 because you're lifting it partly. You're not lifting it fully, a little bit of help. All right? If someone is standing on a weighing scale and you just pull his pants up a little bit from behind, and you'll find that he's weighing less because he's not pushing on the scale with all his complete weight. You understand what I'm saying? When you like lift him off like that, immediately you'll feel that. Or when you're standing on a scale, just push on the table with your hands. So you're getting some extra help. So the normal reaction is not pure on you. The normal reaction on you is not purely by the scale, but is also from here. And that's why the scale will read less. Right? Or if someone is standing on a scale, you just go behind and then push the scale from, like use your toe and push it down. What will happen is the scale will read more. Why? Because it's not the person pushing the scale alone, you're also pushing it. So the scale will push you up with a larger force. And that is what is actually recorded as the weight. So in this case, the normal reaction is only 33.7. That means it's not sitting with all its might. It's only sitting with 33.7 newtons force. How will this impact this problem? Right here. Now can you find out the kinetic friction? Go ahead. How much is the kinetic friction? Kinetic friction is equal to 0.3 times 33.7, which is 10.1 newtons backward. Now we're going to apply the Newton's second law to the x direction. Why? Because we are anticipating an acceleration. So the net force in the x direction is equal to ma. Is equal to ma. So now we are going to look at only the x forces. Forget about the y forces. This box is being pulled forward with 76.6 newtons. So 76.6 forward. Anything backward? Minus 10.1 backward is equal to, that's it. There are no other x forces. Is equal to ma. What is m? 10 times a. Find out how much is a? 6.65 meters per second squared. Do you understand this? So the acceleration is definitely impacted by the way you pull it how much normal reaction ends up acting on the object, and all those. So, do you get this? Any question? Yeah.
So why did you put the NR as negative down there in the blue when you were first solving?
It's not negative. It's positive.
Oh, okay, that's right. It looks like a negative sign.
Where?
That
Where's the negative sign? I don't see it.
That white space?
no,
The negative 98.
Where's the
next
negative?
to the left of the 98. I thought it was saying negative 98.
Yeah, it is negative 98 because 98 is downward.
Okay, no.
You get it?
You're saying NR was the negative 98.
No. NR is a positive one. So let me put it this way. NR is positive NR, negative 98, and a positive 64.3 is equal to 0. Alright? The sign in front of the variable is what is responsible for that variable. So this is a plus sign which is for NR, and that minus sign is for the 98, and that's a plus sign for that. Is that clear? Any other questions? Any other questions? No? Now, how is this whole problem going to turn around if the force is not applied from here, instead it's a pushing force from here? Same 100 newtons, same angle of 40 degrees. Now it's actually a push. You know, you can pull a box with a rope, or just push like that, right? So now we are pushing it with the same 100 Newton force. We drawn everything? Let's discuss the same way. Straight away, go ahead and split that into components. So this one has two components. One is this, and that has got a vertical component that way, see? When you're pushing something down at this angle, when you're pushing something down, this push has two components. One is a vertical force and the horizontal force. So when you're pushing it like that, it does two things. Applying a force from above, and well, the numbers are exactly the same. What is this? 76.6 newtons. And what is that one? 64.3 newtons. So the numbers are exactly the same because this is 100 cosine 40 and that's 100 sine 40. So numbers are the same but just different directions. Now, think about it the same way. The net force in the y direction is still supposed to be 0. The book is not going anywhere. The box is not going anywhere. So, how do you take the list of it? Go ahead, you start. Start the forces. Which one is positive?
98.
Which is positive here? The vertical force. The normal reaction is positive. So plus NR, then minus 98, then minus 64.3 is equal to 0. Just follow the rules, and then that's it. You get your problem solved. Drawing diagram, mark all the forces, split the forces, and after that apply the rules for first law or second law. Simple as that. Students who don't really understand the technique of solving it, they'll get totally lost. The problem is twisted a little bit, they give up because they don't know how to tackle it. So any situation, you just analyze the situation, draw the diagram and go on, and you can just go through it. Alright, so we have this. What is NR equal to here?
62.
162.3, and that is definitely going to make a difference to the friction, which is equal to, what is 0.3 times the new normal reaction of 162.3? 40? 48.7. Right? 48.7 newtons is backward. And this is forward. Look at that. That is forward. And this is backward. That's it. Horizontally, these are the only two forces. So the net force is 76.6 minus 48.7 is equal to MA. Now what is the acceleration? 2.79. You see how the problem just slightly changed. The acceleration is far less compared to the previous one, which is 6 point something. And that simply tells you which is easier, pushing a box or pulling a box. Pulling. If you want to push, scoot a box from one place to another place, which option is better? Like dragging it, pulling it like that, or pushing it like that? Because when you push it, you're actually adding to the normal force. When you're pushing, you're adding to the normal force, and that makes the friction worse. And that is why you're not able to get the actual acceleration onto the object. So it's harder to push. It's even a lawnmower when it's not working. Is it easier to pull or to push? It is easier to pull. You can pull the lawnmower because when you're pulling it, you're partly lifting it as well. So you're freeing it from the friction, whatever is there. Whereas when you push it, you're adding to the normal reaction, which will add up to the friction, which will make it difficult. So it's possible sometimes that when you're pulling it, it's able to move. When you push it, it won't move at all. Why? Because this force becomes bigger than this attempt. So the attempt by you to make it go forward, if this thing can go up to 80 or 90, then you're not going to be successful in pushing it. You get it? All right, I'm just showing some variety of problems, so let's see some other types here. Let's go to inclined planes. Just one more example and then we are done. That's a regular inclined plane problem. You know this thing, right? So when an object sits on the inclined plane, the object of mass m, I'm not giving any numbers there. What are the forces acting on it? Yeah, there are gravitational force, yes, this is mg. But more than that mg, what do? You resolve it straight away. So how much of this is this way? How much of this is this way? mg cosine theta. And how much of this is this way? mg sine theta. These are things that you already know, so put it down. That's going to be there. That's going to be there for all objects on an inclined plane. And it's the same thing. Sine theta, cosine theta. And theta being this. What else could be acting on it? Friction. Now, if this object is trying to drag itself down, then friction is which way? And how much? How much is friction? Mu times normal reaction. And what's a normal reaction? So there is a normal reaction, which is mu times mg cosine theta. So the frictional force that's going to act on it as it slides down is mu times mg. What mu? Mu k or mu s? Is everyone on the right track? Yeah, make sure that you're perfectly on the right track, otherwise it makes no sense. So the frictional force is going to be kinetic. If it's going to move already, then it's kinetic friction. If it's not moving, that's a different thing. But if it's moving, if you're anticipating it to accelerate downwards, then the frictional force is this way, which is mu times mg cosine theta, which is the normal reaction, correct? So, yeah, those are problems that you should be able to do it straight away because you already done something like this. Now, a little twist to the same problem. This is an object sitting on the incline, and this time this object is going up. It's moving upward, or it is made to go upward. It's like this. An object is sitting here, and you're going to make it go upward. So you're going to apply a force like that, up the incline. So if you apply a force that way, and make it go that way, which way is friction? How much? How much? Tell me an expression. Yeah, mg, mu times mg cosine theta. Is that clear? But so if I give you an applied force in that direction, and if I tell you that this thing is sliding upward, then you can actually immediately switch the direction of friction this way and then start working on it the same way, right? So in that case, how many forces acting on this? F is acting this way, the one which you applied. Mg sine theta is acting this way, and friction is going to act backward, equal to Ma, right? So you set up your equations that way. Now, giving it a further twist, I'm not pushing this object along the incline. Instead, I'm going to push the object horizontally like this. See? Do you see the push? Not along the incline. I'm pushing it like this. It's almost like you have a ramp and you're pushing an object that way. You're pushing it horizontal. So in other words, I'm going to push this box with a force which is a horizontal force. So I'm going to push it that way, not this way. If you're pushing it along the incline, that is easy. And if I'm pushing it that way, what's going to be the consequence? Okay? What is going on now? If you push it in that direction, see, already you know when you are talking about an inclined plane, you're talking about this as your x-axis and this is your y-axis, right? You are imagining it that way. Now, with respect to this as your x-axis and that as your y-axis, this is not acting along the x or y. So what do you do first? Resolve it. Since this angle is theta, this angle is also theta. Now tell me how much of this f is acting this way? How much of f is acting this way? How much of this f is acting up along the plane? F what? Cosine theta, because this side is adjacent to theta. So always look at that term adjacent or opposite. That will tell you what it is. So this f has two components. One is f cosine theta this way and f sine theta that way. Or you can actually look at it here. So this f sine theta is this way and f cosine theta is this way. Make sense? So instead of drawing the f sine theta here, I draw it here because that's the object on which it's acting. So it's better to draw it on the object rather than anywhere else. So f cosine theta, f sine theta, which is same as this. That's the only difference. And after that, you think about everything the same way. Now, is this normal force mg cosine theta just like before? No, because now there's something else coming in. So what do you do now? Apply the first law once again. Net force equal to 0 in this direction, which is what we call as the y direction. So list it up. What is the force that is positive? NR is positive. What else? Anything upward? No. There are two forces that are acting downwards. That is this. So minus mg cosine theta minus f sine theta is equal to 0. So what is NR? What is NR? mg cosine theta plus f sine theta. That's your new NR. Previously it was mg cosine theta straight away. But see that the normal reaction can be affected by some other forces. You see, when this force came in, there is a new normal reaction. You're pushing it furthermore. That's what it implies. See this? You can see the clear difference. When I'm pushing it from here, it was easy to drag it out. But when I pushed it from here like that, it is harder to drag it. Why is it harder to drag it? Because I've increased the normal reaction, which automatically is going to increase the friction. Which way is the friction? Which way is the friction acting here?
Down to
Yeah, because you're expecting it to move that way. Friction is this way, and how much is friction? It's mu k times the new normal force. That's the force. Now what do? Apply your second law. Net force is equal to, net force in the x direction is equal to ma. Now, you know, remember this, when you're applying net force in the x direction or whatever is equal to ma, when you're applying the second law, it's better to take the bigger minus the smaller equal to ma. Don't go for sign conventions, it will confuse you. Okay? It will confuse you more than anything else. So therefore, the bigger minus, which way is it expected to go? We are expecting it to go that way, because you're pushing it up the plane. And therefore, which forces must be bigger? These are the bigger forces, right? And these are the smaller forces. The ones which are against the movement are the smaller forces, equal to ma. So let's list it. Which are the forces acting in this direction? F cosine theta, that's right. What else is acting in that direction? Nothing. See, only F cosine theta is pushing the box up like that. And there's nothing else pushing the box up. What are the forces acting backward? How much? Yes, so it's minus mg sine theta, that is this force, that's component of the weight, and you have the frictional force, which is minus mu k times the new normal force, that is mg cosine theta plus f sine theta. And that is equal to ma. That's our equation. So this is the force forward, this force is backward, that force is backward, is equal to ma. I know the equation looks kind of big, but if you're using numbers, it should be much easier, right? So if you had a multiple choice question saying, well, this is the situation, what's a normal force? And you're given 4 or 5 options. Normal force is mg cosine theta, or normal force is mg cosine theta minus f sine theta, normal force is mg cosine theta plus f sine theta. You know, something like that. You should be able to figure out which is actually the new normal force by just looking at that. Any questions? And that is the expression for the net force equal to ma. Net force equal to ma. Now, we have not used numbers here, we just use only variables. And if numbers are involved, then it will be easier, okay, because we don't have all that stuff. Yeah, so you can see how different the problem is going to be just because the force is coming at an angle, okay? How do you practically find the coefficient of static friction? Right? Practically, how can you find the coefficient of static friction? So if I want to know what is the coefficient of static friction between this surface and between, that's it. So if I want to know what is the coefficient of static friction between this object and this surface, so what you do is this. Yeah, you're going to put it on an inclined plane. So when you put that object on the inclined plane, what are the forces acting on it? Is it moving? Is it moving?
No.
No. Why is it not moving? Let's discuss that. What is the force acting on this? Yeah, there is mg acting, but I'm not going to just draw that at all. What is this? Mg sine theta. What else? What else is coming in? There is a normal reaction. I'm not going to write that also, because we are concerned about this movement right now.
And friction.
Friction. How much is friction? Is it static or kinetic right now? Static friction. And how much is static friction?
UK and mu s.
Let me see if you can answer that correctly. What is the static friction right now? What is the static friction right now? Huh? Mg sine theta. Why? Why?
Because it builds the static friction.
Static friction builds up from, what's the static friction right now? Nothing. Now there is an attempt by this to go down with the force of mg sine theta, but the friction kind of says, no, I'm not letting you go, and therefore the frictional force builds up to the whatever is attempting to make it go down. That is mg sine theta. Now if you tilt it more, then it won't go down again. That's because mg sine theta is telling it to come out, but this friction says, no, I can still withstand it. So if you keep on doing this, there may be a time if you increase the angle, if you continuously increase the angle, there will be a time when it starts slipping off, right? So what is that moment? When it just starts slipping. When it just starts slipping, so probably at this angle, it just started slipping. So we are going to discuss now the point of slipping. When it just slipped, the force downward is mg sine theta. And what's the force upward? When it just slipped. What was the force at that last moment? It is mu s times mg cosine theta. Is that clear? That is a limiting value, the maximum value. The maximum value of static friction. The maximum value of static friction is mu s times normal reaction. That's a maximum value. This is the maximum static friction. The limiting value of static friction. So the moment it started slipping, it implies that this just overcame that. Get it? Let's say the limiting value is like 10 newtons. So when this was like 2 newtons, that will be 2 newtons. And this is 8 newtons, that's 8 newtons. When it's 9.9 newtons, that's 9.9 newtons. When this reaches just 10, that let's go. Okay? Because it reaches maximum, it can't hold any further. And so what do you understand from there? At that situation, the moment it starts slipping, and you can see that as after it started slipping, it slips and falls off, it easily accelerates. Because okay. Yeah.
Just the kinetic friction.
Exactly. Once it starts slipping, it becomes kinetic friction, which is lower than static friction, so it will just fail. Do you understand that? So at this point of slipping, you can clearly say that mu s mg cosine theta is exactly equal to mg sine theta. Is that clear? Until this angle is reached, the backward force was mg sine theta, whatever it was. But now at that moment, it is now the maximum limiting value of friction, which is this. You look at that equation, you can just knock off this, knock off this. And what is mu s? Sine theta over, which is? All you do is just find that angle and find the tan of that angle. The answer is over. So the moment it slipped, suppose I'm inclining it gradually. Got to do it very, very, very gradually. And the moment it actually started slipping, the moment it actually started slipping, pause. Measure the angle. Now how do you measure the angle? Using a protractor, or protractor is not something that you commonly have, or, so how do you measure this angle? This is the angle, I froze it at that position. And then how do you measure that angle? Use a meter stick. Measure this side and measure this side, or you know the length of this thing. You know the length of this. And it is resting down there. So you know the length of it, and you know the height. What else you need? So if you know this height, and you know this, how do you find the angle? You know this height, and you know this length. What is sine theta? H over L. So you can figure out the angle, and then put it down here and find the tan of that angle. So if the angle turns out to be something like 35 degrees, what is your frictional coefficient? How much? If 35 degrees is the angle, if theta is 35 degrees, what is the frictional coefficient? How much? 0.7. No? Are you sure? Yeah. 0.7. The coefficient of static friction between the objects is 0.7. So that's one fast way of finding it out. Now how do you find the kinetic friction now? The coefficient of kinetic friction, if you want to find out, you do the same thing. You do the same thing, but this time you kind of tap it like that and make it go at a constant, moving at a constant velocity. Make it go at a constant velocity. When you make it go at a constant velocity like that, not accelerating it, freeze it there, find the angle. And find the same tan theta. Make sense? So the first one was it's at rest, and you kept inclining it till it slipped. And you can see it's accelerating. The second case is like you are tilting it, but all the time you just kind of slightly tap it and make it go at a constant velocity like that. Make it go at a constant velocity like that, not accelerating. Then you apply the same thing. So if that angle is like 30 degrees, then it will be tan of 30, whatever it is. 0.57. How much is tan 30? 0.5771.
0.577.